In the last video, we discussed the different scenarios for two planes intersecting, and we also looked at normal vectors as a way to determine which case we have. So we noticed that if normal vectors are parallel, then planes are parallel, and then we just had to look a little further to see if the planes were distinct or coincident. And to do that, we looked at d values. I'm going to take a slightly different approach in this video and actually just forge ahead to find the intersection points. Now for the first two cases for two planes where they're parallel and distinct, case A, or parallel and coincident, like case B, we could use other methods like the normal vectors and the d values. And that's probably more efficient to do it that way. But I also want to look at the algebra of solving a system of equations, in this case two equations, with three unknowns or three variables. And the techniques we will use here will help us both in case C, where we do have to find an intersection, the line intersection, and also when we move to looking at intersection of three planes. So let's take a look at case A. So we already know that if we tried to solve this system of equations, we should get no solution, because we have two parallel planes and they're distinct. They do not intersect at all. So the method that we're going to focus on here is using elimination to solve the system. And I know some of you like to use substitution. You've avoided elimination. But now that we have more variables and soon we'll have more equations, elimination is a much more organized and efficient way of solving a system of equations. So if I look at this system of equations, I'm just going to proceed first of all by eliminating x. So my first step here is eliminate the x variable. When we're using elimination, it's good to keep track of what step we're doing, and for communication we want to clearly state what we're doing at each stage of the process. So first of all, I'm going to label the equations. So equation 1 and equation 2. And I'm going to eliminate x in equation 2 using equation 1. So I want to think about using this 2x to wipe out this 3x. Now I can't just subtract directly because the coefficients are not the same. 2 and 3 are not the same. So I'm actually going to multiply equation 1 by 3 and equation 2 by 2. And I'm going to document that on the side. So I'm going to write 3 times equation 1. And so I'll end up with 6x minus 18y plus 12z minus 21 equals 0. Then I'll multiply equation 2 by 2. So I say 2 times 2. Notice that I'm using a circled number to identify the equations so I don't mix them up with my coefficients or my numbers that I'm multiplying by. So 2 times equation 2 will give me 6x minus 18y plus 12z minus 4 equals 0. And often what I do is I relabel these equations. You can call them equation 3 and 4. I like to put a little dash to say what equation they came from. So now I'm dealing with equation 1 prime and 2 prime. So my next step is to subtract these equations to eliminate the x variable. So I'll have 1 prime minus 2 prime. Notice what happens here. I eliminate the x term, but because the normal vectors were parallel, I end up eliminating the y term and the z term. And so all of this becomes 0. I end up with 0x plus 0y plus 0z. And then when I subtract the d values, or just the constant term, I have minus 21 minus minus 4 is minus 17. And that's all equal to 0. So I end up with an equation that's all zeros for the variables, and a minus 17 is equal to 0. Now clearly that's not possible. minus 17 can't equal 0, so our conclusion is that there's no solution, because we can't have negative 17 equal to 0. So regardless of looking at the normal vectors and the d-values, as we did in the previous video, we could just forge ahead and do elimination, try and solve the system, and we end up with something that confirms that these planes must be parallel and distinct, because there's no solution to the system. So let's take a look at the next situation. Already we know that we should have an infinite number of intersection points. So if I proceed with elimination here, I'll label this equation 1. This is equation 2. And I'm going to multiply equation 1 by 2. So I have 2 times equation 1. It's 2x plus 2y minus 4z plus 4 equals 0. And I'm just going to rewrite equation 2. So I'll call that equation 1 dash, or 1 prime. Equation 2 is 2x plus 2y minus 4z plus 4 equal to 0. Notice what's happened here when I scaled equation 1 up by 2 so that I could do elimination. Every term is the same, even the d-value. And we found that in the previous video, that the d-value was scaled up by the same scalar as the normal vectors. So now when I do equation 1 prime minus 2, I end up with zeros everywhere. So my conclusion here is that, the final step here is that 0 is equal to 0. So my conclusion is that this is true. So it means there are intersection points when I consider both of these equations together. But this doesn't tell me anything. In other words, there are no restrictions on x, y, and z. Therefore, x, y, and z have no restrictions. The only exception to that is that they actually have to satisfy the original equations. So if I go back up to the top, as long as x plus y minus 2z plus 2 equals 0, then I will have a point. As long as x, y, and z satisfy this equation, I'll have a point that lies on both planes. That's what this 0 equals 0 is telling us. And what that really means is that the intersection of the two planes is just one of the planes. So this plane equation, this scalar equation, is a description of all the intersection points.